Welcome to this NPTEL lecture on ultra wideband antennas. While discussing broadband antennas, we said that there are log periodic antennas, spiral antennas, etc. They are broadband, but they are dispersive in nature. So, a pure pulse of very short duration, typically of nanosecond or picosecond duration on time, that cannot be passed through and that type of antenna. It will have severe distortion, but today we will see both various types of ultra wideband antennas that can pass that type of pulses, and we will not go into the details because these are quite advanced topics, but to have a glimpse of the applications of these antennas and requirements, why these antennas are being developed, for that today we will have this lecture. So, the first we start with the first slide, that what is the definition of ultra wideband. Actually, there is a lot of debate over this, and IEEE still now does not come up with the proper definition of ultra wideband, but FCC, Federal Communication Commission, they have already came up with a correct definition, scientific definition of ultra wideband. So, we will see that according to that a signal is called ultra wideband if the fractional bandwidth is greater than 20%. What is meant by fractional bandwidth? Actually, this is the new thing, that fractional bandwidth is basically, because for ultra wideband signals there is no question of center frequency. So, there is a low frequency of operation, there is a high frequency of operation. So, they are defined as typically 10 dB from the maximum. So, FH is the highest frequency at which 10 dB from the maximum of the signal is there. Similarly, FL. So, it is FH minus FL by FH plus FL by 2. So, that gives it the branded definition, and alternatively also a ultra wideband signal should have at least the absolute bandwidth should be greater than 500 megahertz. And if we again look at this bandwidth definition, please note that we can easily find out that what is the maximum bandwidth that is possible. So, theoretically the maximum will come to be from this one, because FH and FL both should be positive frequencies, or actually FL should be positive frequency. So, that shows that 200% is the maximum that any signal can have maximum bandwidth. So, an ultra wideband signal, its maximum bandwidth is 200%. Now, we see that these are typically impulse like signals, but actually they are short pulses of duration few nanoseconds. So, obviously, if they are so short in time, they occupy large bandwidth. Then these are in communication, this UWB, you can see that these various applications where these are required. So, this is UWB communication. Obviously, this type of short pulses, they do not go much distances, their range is limited. So, initially their range was only some few meters, that is why you see all these applications are very close distance things, the range is not much. But nowadays in consumer electronics, mobile devices and PCs all have UWB broadband connectivity built in. Typically UWB devices may operate, not typically, but excess of 1 Gbps is quite natural nowadays, and their range is possibly 50 meters. So, from few meters up to 50 meters people are using it, but they are unmodulated signals, directly the pulse is getting transmitted. Obviously, there are lot of attenuation, that is why the range is limited. But other UWB communication applications are for wireless sensor networks, typically 100 kbps, less than that speed. So, monitoring office and residential environment, then plant monitoring, security monitoring at airports, etc. Then wireless BAN, body area network, communication between two body owned devices, they are also people are using it. Then for some emergency purposes, like after avalanche, earthquake, if no communication is there, to establish communication, this is used. Then communication by fire department and law enforcement agencies, etc. But more than communication, actually this technology has so many other applications. So UWB technology, particularly in the form of radars, which are a different kind of radars than the conventional radars. So UWB technology can be utilized for seeing whether there is any buried unexploded ordnance. Actually, in an war-torn country, there are many mines, etc. kept. Also, sometimes many arms, ammunitions, some IEDs, etc. they are kept, and later when the war is over, that poses problem to civilian people. So detection of that is a UNO's job. So this is required for that. Then UWB technology is also used for seeing whether anyone is there behind wall, through wall imaging it is called, anyone behind foliage, whether something is buried inside ice. In various mountain warfares, these are required. Then in case of, in our country, in winter season, whole North India, the railway movement gets disturbed because of fog, etc. So within fog or during fog, can the rail system or transportation system go unimpeded? UWB technology also is used for highway health checkup, highway inspection, underground utility like water pipes, etc. What is their health, whether they are leaking, then building, whether that will fall down or not. In mines, the mining industry, mine roof health, whether it is okay or it will fall. UWB technology also is used for subsurface water detection for agriculture. It predicts how much the growth of any crop will be there. So various also lot of industrial uses to find out the crane movement, exact position of the molten stuff. So lot of things UWB technology is used. Some of the examples I will hurry through. This is buried object detection. Then what I said, that this type of mines are there. So can we detect it by this UWB technology? Then through wall imaging, whether someone has taken some hostages. So people want to see, police department want to see from outside who is there inside. Then suppose whether behind any wall someone has kept some rifles, or whether some person is thereby. So suppose this person is behind this wall, from the other side of the wall this image shows that okay, there is a person. Then these are all various this rifle, so it's various pictures. Then there are also that suppose in the space you want to have an inflatable antenna. Nowadays people are using that after going to space the antenna will be flown. So can it have that UWB technology? Then orbital debris, lot of orbital debris are flowing. So can anyone harm us? So for that there is a need for detection of that. Then suppose someone is trapped under some avalanche. So can we detect that whether he is some person is trapped or under debris of some building collapse. Also whether the person is live or not, that is an active area of research. Then an aircraft, can we fully take an image of that aircraft as we take from optical cameras. So for that this is required. Now, so if we see various applications, there are basically two types of application. One is high power or low power, like communication, subsurface detection, health checkup for various utilities, that requires low power systems. Whereas there is a thing called nuclear electromagnetic pulse or lightning, electronic warfare, E-bomb, etc. requires that whether your electronic system is susceptible to that or not. So, that is called vulnerability testing against electromagnetic pulse, that require high power systems. Actually, basically the second thing, high power systems, that was a Cold War time thing. So, that time while trying to answer these questions or trying to develop these systems, people came out with the high power develop these systems, and on developing that system actually came the high power UWB antennas, but low power is a more, you see, civilian type of need or internal security type of need, and it is now those applications are coming up, and people have also come up with low power UWB things. So, question is that to have this cater to this technology, we need antennas. Now, both high and low power systems require UWB antennas at microwave frequency with more than 100% bandwidth. That means, if microwave frequency typically you can say 10 gigahertz. So, that means I require a bandwidth of 10 gigahertz. So, in a 10 gigahertz frequency of operation, if I require 10 gigahertz, or can it have 20 gigahertz type of bandwidth, that means 200% bandwidth? The answer is fortunately yes. People have come up with such type of things, may not be 200%, but very close to 200%, that we will show today. Now, first we will see the high power UWB antennas. The first one was developed in 1995. It was developed by three scientists, Carl Baum, D.V. Giri and Everett Farr. Actually, it was developed at Air Force Research Laboratory, Kirtland, AFB, New Mexico, and Protec is a firm which supplied that, but that whole design etc., whole research was carried out for almost 20 years, and then that culminated in this. So, that is why in these three persons, they got the John Cruz award for antenna, this antenna development. Actually, this is the first time they have shown that a nanosecond type of pulse non-dispersively can be sensed, and this is the picture of the first developed this thing. This is called impulse radiating antenna. Now, this is the more clearer view of this. So, you see there is a paraboloid reflector. Actually, there is a, this is called some launcher, wave launcher, and so we will see the this thing scientifically. So, there is an excitation source, it is a very high power excitation source, it is a pulse excitation. Then there are these feed arms, they actually take that wave and they are actually should carry TEM wave, they do not allow the wave to the TE or TM mode to come, because if they come, TE and TM mode have a cutoff. So, they cannot have a wideband characteristic. So, this, and then the on parabolic reflector they fall that thing, and after that, that becomes a plane wave. Also, there are some terminating loads at the ends, these are for cutting, if any by chance high frequency components, undesired components comes, to cut that. So, basic building blocks of an IRA, one is a pulsar, that they call that pulse source, it is a high power pulse. So, then there is a TEM wave launcher, then there is a reflector, you can have any type of reflector, but preferably paraboloids are used, and then some terminations. Now, TEM wave launcher design options, it can be a bent circular cone, it can be coplanar plates, modified coplanar plates, or asymptotic conical dipole plates. This is a very modern thing. So, we will see that bent circular cone. So, this also, this can launch TM waves, or this is coplanar plates, planar plates, but coplanar. Now, this is modified coplanar plate, and finally, ACD, asymptotic conical dipole feed, this is the thing. So, actually conventional IRA was designed from coplanar plates, but it was found out that it has an input impedance of 200 ohm. So, ACD also can give you that, but the beauty of asymptotic conical dipole is that it can be amenable. So, you can make IRA with any input impedance. So, here it is showing that 200 ohm, but this is the comparison, and it can be proved that this ACD fed things that gives a better gain also. This is a return loss, you see typically 10 dB is the impedance bandwidth, and this is the electric field how it looks like for a given very nanosecond type of a thing. Then this is the gain. So, the ACD fed that is better compared to a slightly better. Now, IRA basically needs a Belan typically, because the conventional IRA that was designed, that has an impedance of 200 ohm. Now, pulse generators, generally electronics industry produces generators with 50 ohm. So, also pulse generators are single ended. So, getting a 200 ohm line is difficult. So, a 200 ohm to 50 ohm Belan needs to be added, and also any Belan will produce some power loss which is undesired. So, the question was that people have modified the IRA so that the Belan is not required. So, you see that with ACD you can design a 100 ohm impedance also. Similarly, now if you have a ground plane, and if you have half of the IRA, that is called HIRA, half impulse radiating antenna, then to get rid of balloon you can use this. So, 50 ohm to 100 ohm impedance can be achieved from this. This is a half HIRA. This is its input impedance. So, you see 100 to 50 ohm it is varying, certain times it is going even below 50 ohm, but this is good with the thing, and this is the excitation. If you give an excitation of this is the measured voltage at a distance. So, you see that faithfully it is reproducing this, there is no dispersion here, and this is the impulse response of the HIRA. So, this is all IRAs etc. requires this. So, very low ringing, and you see that successfully it is giving a good impulse response. That means, if you give an impulse it gives. Now, you can say that impulse is one sided, but why there are two? Actually, that will always come, because actually in the far field the while the wave is getting launched, there is a direct return that gives you this one negative side, but with that this positive side is enough to say that there is an impulse present. Now, these are the various terminators. You can have metal film resistors, or you can have carbon composition resistors etc. So, that was about high power thing. Now, low power UWB, you see one typical application of low power things are making ground penetrating radar, which all the applications I have said about this except communication, they can be done. So, various options are there. There are printed monopoles, rugby ball antenna, then there were Vivaldi antennas, there were bow tie antennas etc. So, we will see them. So, what is the requirements of a GPR antenna? Actually, it requires ultra wide bandwidth, because any range resolution is inversely proportional to the bandwidth. So, greater you get the bandwidth, you get the resolution. So, get very fine resolution, we want UWB type of bandwidth, that 10 gigahertz etc. type of. Then also GPR wants low frequency operation, because it needs to penetrate the ground or any material wall etc. So, for that it also should have a low frequency up to the FL, that should be quite low, typically in the order of megahertz, 300 400 megahertz like that. Then also it should have high front to back ratio, that means back lobe should be reduced, because GPR always see below the ground. So, why unnecessarily power should be there in the thing. And also if any gain is, obviously better gain means power requirement will be less or more range in the ground. So, these are the 4 requirements of any low power GPR type of antenna. So, there are comparison of GPR antennas. One is TM horn, it is a simple horn. Point is, it is also gives a non-dispersive thing, it has a good directivity, but problem is its size is very big. Spiral antenna, we have already discussed about this, it is dispersive, that is why it creates problem. Impulse radiating antenna also sometimes for this low type applications may be used, but again the problem is that its size is quite big. Then there are tapered slot antenna, which is commonly called Vivaldi antenna. It has good both side directivity and low side lobe level, but its problem is its radiation is end fire. That means maximum radiation takes place in the end fire direction. So, in some applications it creates problem, because then the size of the thing becomes quite large. Also it is also non-dispersive, it is ultra wideband. Then there are various types of planar monopoles and dipoles, but sometimes they becomes dispersive, etc. Now, let us say one of the antenna, rugby ball monopole antenna, its bandwidth you see 0.3 gigahertz to 2.5 gigahertz, and fractional bandwidth from that definition if we calculate, it gives 157% bandwidth. Its polarization is linear, directivity is omnidirectional. This is the impedance bandwidth you see from 0.3 to 2.5, it is working. Another option is bow tie antenna. Actually, this type of, this is a dipole, from that actually people have modified this and then put some resistive loading to cut off various high frequency undesired things. Then there are, instead of loading at the lumped ones, people have also loaded here. So, this is one in civil engineering, various applications like health checkup of various buildings, infrastructure health, this antenna is used. Now, there is also one RC loaded bow tie antenna. So, in the in this one, this is a planar one, the RC loading is kept inside the antenna's conducting plane itself. Its bandwidth is 0.3 to 3 gigahertz, fractional bandwidth compared to the previous one 163%. You can see this is the graph. Also, if you give an input signal like this, this one gives you signal like this. As I said, always you see, if you give an impulse, it will have this double sided thing, that is typical of any antenna, because antenna in the far field actually puts derivative. So, there are one signal is going up, another signal is going out. So, if you take the derivative, you will always get this positive peak and negative peak. Now, this is a fabricated RC bow tie antenna looks like, and this is the simulated results for its S11. This is the realized gain, that things. Finally, also you can put some lenses to better the back lobe radiations. So, this lens design is again from the surface equivalence principle that we have seen, and so this is a people are nowadays using metamaterial lens. Metamaterial has a property, actually metamaterial means which does not exist. Actually, for metamaterials, out of mu or epsilon, that means the permittivity and permeability, one of them is negative. That gives us various properties which are not found in existing material. So, it is a planar array of some cells, it is a periodic structure, one cell looks like this, and then if you have, so you see the this back one, this is the antenna plane and there is a lens in a different plane. So, this is the model. So, RC bow tie with metamaterial lens, this together makes an antenna, it gives various improved properties, and so you see that with return loss is measured return loss, you can see that within 10 dB starting from here to here up to 3 gigahertz, that means impedance bandwidth is 0.3 to 3 gigahertz, quite good. Then front to back ratio, you see with lens and without lens is shown here. So, front to back ratio maximum is 15.39 dB, that means it is cutting the back radiation by 15.39 dB at 1.46 gigahertz, and better than that of without lens at all frequencies. So, putting the lens helps, that front to back ratio is improved, and both side gain, you see gain maximum with lens is 11.52 dB. This is quite significant for a GPR antenna, and gain max without lens is 6.45 dB. So, at least 5 dB improvement in the gain at frequencies above 2 gigahertz was given by the lens. Then people came up with another thing, that instead of RC loading, if you load with a loop. So, this is a loop bow tie called. So, evaluation of loop, that these were loadings, this is suppose the actual antenna and you are loading like this. So, if you consider that these two, if you join, it becomes something like this. So, this is a bow tie antenna loaded with a loop. So, this is the fabricated antenna, these are some results, and the radiation pattern. Now, one of the thing is, all these UWB antennas, they had one problem before all these modern antennas came, that at lower frequencies they are always having bore side maximum radiation, but after certain frequency they start tilting, the main beam starts tilting. But this one, you see that there is no tilting in the throughout the whole band, there is no tilting. Now, that makes actually whatever impedance bandwidth was giving, the whole bandwidth was not usable for UWB antennas. That is why there is a term called useful bandwidth. So, it turned out that all the planar antennas, UWB planar antennas, were suffering from this. Now, this one seems that it has make that, and also you can put some directors. You see, instead of one there are more loops. So, that gives the director sort of thing. So, this is a fabricated antenna, loop loaded bow tie. These are the various design parameters, and this is the with directors, this is the radiation pattern. You see the radiation pattern is changing at various frequencies, but the maximum radiation is always at the both side. So, that makes it that is why you see here it is listed that various contender for this bow tie antenna, the bandwidth, you see that 10:1 is typical. 10:1 means if you have a 500 megahertz, then your low FL is 500 and your FH is 10 times that, that means 5 gigahertz. So, that, but unfortunately that RC loaded bow tie, that has a useful bandwidth 4:1, because that means after 2 gigahertz the beam will start tilting. Now, you see other things also people have come up, various, these are various references. So, where people have come up, people have gone to 250 megahertz, but you see 3:1 was the bandwidth, and also size is a factor, because for these systems the smaller size is good. So, RC bow tie can give you 10:1, that has been improved to 5:1, but then if you put the lens, then that becomes 5:1 becomes 7:1. You see other things are more or less same, but loop bow tie, you see 500 megahertz, this 10:1 has been changed to 11:1. That means the bandwidth is increasing, and loop bow tie plus directors, you see it is going lower, and also 13:1, this is the best till now achieved, and also the usable bandwidth is full this impedance bandwidth. So, that is a remarkable improvement, and this is a very good GPR antenna. So, hopefully this will have a lot of applications in future. So, with this we have seen that various UWB antennas, there are various characteristics how to make that, and this is an active area of research. Hopefully, people will come up with better and better antennas after this. So, with this UWB antennas, we have shown that you can have by giving the picture that you are giving a pulse excitation, very narrow pulses of picosecond duration, but you are also getting the radiated signal is also like that. So, there is no dispersion there. So, these are promising things. Hopefully, you people also will have better such antenna design, but basics whatever we have seen, that helps you to design this type of antennas. So, we conclude this lecture here. In the next lecture, we will see what is the how to measure various antennas characteristics. So, antenna measurements we will concentrate there. Thank you.